Power series. Power series are polynomial functions, and they're really important tools for us to deal with complex math analysis. And they're very useful because they allow us to calculate decimal values for things that are like exact values. For example, log 2 is an infinite decimal. To actually calculate that infinite decimal is really hard to do, and power series allows us to do that. Another example would be to calculate the actual value of pi. Okay, that's really hard to calculate an infinite decimal for, to get the actual decimal value for that. But the power series gives us a tool that allows us to find these decimal values to any decimal we want. We can go as many decimal values of accuracy as we need to. Now, these power series are polynomial series, and they're built of two parts. They're built of an AN part, which is an N series or a coefficient part, and then also have an XN part, which is our power series or the polynomial part of that. So these two parts together make a power series. So these power series are series, and because they're series, they're an infinite series, they have to converge. So it's really important that these things converge. Now, because they're built of two parts, an AN part and an XN part, these series are dependent on some values. They can be dependent on values of x for them to converge or diverge. Now, because they're dependent on x for convergence and divergence, this also will give us the idea of the domain. X is the domain or the input of the function. So when x is some values of x that converge, that allows us to determine the domain of the function. So in the domain, the function will converge for values of x. Outside of those values of x, they will diverge and therefore won't be part of the domain of x. So these series, when we expand them out, they represent functions. So we can say that this expanded series, when we write out the terms of series, f of x, so our f of x can be equal to, or f of x is equal to the terms of that series when we expand. So when a is 0, we have just x to the power 0, which is 1. A1 represents that a and the sequence part of that. The n sequence part of that represents the coefficient. Then we have the power of n. And as we write the terms of this, we generate a polynomial function. And as we add more terms, the degree of the polynomial gets higher. Okay, and again, these power series can converge or diverge. Together, the AN and the X part will make that converge or diverge. So it can often be dependent on different values of X. And what these power series functions do is they actually end up mimicking other functions. And depending on the domain at which they converge, they're going to represent those functions in the domains that they converge in.